Morning, everybody. So I've got a little cough. It's a teeny weeny cough, so it might irritate you a little bit. So I do apologise in advance. So welcome to non-ionising radiation safety. And there was a lovely gentleman. He still is a lovely gentleman, Chris Cooper. I was doing a bit of work for him in the Northeast, and he said to me, "You know what, Raj? This is a subject that not a lot of people know about. So would you mind doing a kind of a talk or a webinar?" I thought, yeah, of course, Chris. Chris is such a lovely chap. I thought, yeah, great. And then I thought about it and thought, oh, crikey, this is quite a big subject area. How do I condense that into an hour? Because there's just so much in it. I think Chris is not here today. So I know you're going to be watching this recording back, Chris. So big thank you to you. So as Lee's introduced myself, as a director and a qualified laser protection advisor, et cetera, one of the things that I'm acutely focused on, it's not just the responsibility of my clients, but it's all the responsibilities as a director to my colleagues and the people I work with as well. And so as an employer, we're affected by sources of non-ionising radiation in the workplace, or NIR, as I'm not going to effectively call it. And it's trying to get that corporate approach across that Lee mentioned. A lot of this stuff is manageable, but it's how you go about managing it. That's the key thing, right? Do you do too much, or do you do too little? Do you ignore it? Do you do robust steps at the top, which makes your job easier, and lower down when you set up a structure? So it's trying to introduce the subject and then give you effectively a path going forward. Lee, I think your mic is on. I think somebody's just mentioned that. Marvellous.
Yeah, so somebody's mic was just on there, but I've just muted them.
Lovely. Thank you. Right. So going forward, so Aurora, very briefly about Aurora. We are a private firm, and we are the UK's #1 provider of radiation protection services, and we do what we call ionising and non-ionising. So that covers obviously radioactive material and X-rays, which is the kind of traditional stuff, X-rays and gamma rays and all that fun stuff, but also non-ionising. So we do everything from kind of consultancy through to monitoring for radiation in facilities, to remediating, decommissioning those. We even design facilities as well. Our team in the Northeast helped design the UK's first proton beam therapy unit in the Christie. So they did a lot of shielding design for that, and then we went and tested it as well. But obviously today I'm primarily focused on kind of the training and the radiation, non-ionising radiation safety element. We are, as a central office, based in Harwell, which is in Oxfordshire. But as I said earlier on, we've got a team that's based in the Northeast as well. So today is really to give you an introduction. I can't go into massive detail in an hour because it's such a broad subject. You can actually take non-ionising radiation, or NIR, and divide it into about 2 or 3 segments, and then you can be an expert in each segment. So it's quite different to the traditional radiation that we're used to hearing about, used to seeing about. So I just want to introduce it as a concept, and then talk a bit about the effects on the body. And the big thing about this stuff compared to the other types of radiations is the indirect effects are often more dangerous. So actually the effects on the body can have an impact on people, very unlikely to lead to fatalities, but actually it's the indirect effects which are incredibly dangerous associated with this stuff. And that's the thing that you have to think about when you go and trying to deal with NIR safety. I appreciate that there's people who are outside the UK, but one of the things that Chris and I talked about was I'd actually try and get across the applicable legislation in the UK and how it applies here. But there is commonalities in where it originally comes from, the international environment. Then the risk assessments and control measures. And then people ask me this question a lot: how do I assess exposures from this? Do I need to assess exposures from this? And we'll touch on that subject as we go through, because the reality of it, it's quite a difficult thing to assess. So NIR sources are everywhere, and you will come across them. You probably sat somewhere right now and you've got an NIR source. You've got your computer screen in front of you that's giving off artificial optical radiation. Your mobile phone's close to you, that's giving off radio waves. It's receiving and transmitting signals. You've got all these things that are in the working environment, but are they all dangerous? And the answer is the majority of them aren't dangerous at all. But actually, which ones do you know are dangerous? And that's the real big challenge to this. So when we talk about non-ionising radiation, we're talking about optical radiation, we're talking about electromagnetic fields, and they're very different. in how they interact with you. And I'll explain that as we go through. And that's the big challenge as an employer. You're looking across, say, multiple, you could be a huge organization with thousands of employees who could be affected by NIR. And you're thinking, well, which ones do I need to spend my effort on? And thankfully, there's some really good guidance which helps you. And I'll point that out to you as we go through. And there can be in any environment yourself, just pick three here, really. So there's a mixture here of electromagnetic fields and optical radiation. So the top one on the left is what we call a magnetic stirrer. Pretty much in every laboratory that you do in and experiments, it just kind of mixes a compound in a beaker solution. Got a little magnet inside it, and it produces quite intense localized magnetic fields. Now, are they dangerous? Well, to people who are working in that environment, unlikely to be dangerous at all. But they can potentially have an effect on those who are vulnerable, and we'll call them workers at particular risk or employees at particular risk later on. At the bottom left, you've got a UV Trans Illuminator, and that's another laboratory-based equipment, very cheap to buy. And effectively, what you do is you close the Perspex screen down, and there's little UV lamps underneath, and it sends emissions through. And it illuminates samples which you can put on top. But if you lose the shielding to that, they can pose a real risk to you. How do you use that? What implementation of control measures do you put in place? And on the right there, you've got welding, which presents optical and EMF risks because they've got both. You've got bright lights. We all know about archi and photokeratitis and all those things for years, but actually produces quite an intense magnetic field as well when you're there as well. But again, does it affect welders? Well, unless the welder's got a pacemaker or something, unlikely, but they're pretty strong fields. But let's take a step back. Let's kind of introduce what NIR actually is. So if you think about the electromagnetic spectrum, and you don't have to be a physicist to get all this. You really don't. I think that's the first thing I just want to blow out the water. You don't need to know the ins and outs of electromagnetism. Don't need to know it. All you need to really understand is kind of the different effects that come from it and where the thing comes from. So if you think about the electromagnetic spectrum, what you've got there is on the left side is high energy. So the spectrum is full of, it's like a family of radiations. They're all connected. They're all very similar in many ways, but how they behave is very different. And that's the way to think about them. And they have different characteristics. So on the left there, you have high energy, high frequency, but low wavelength. And so for those you can remember your physics days, you can probably remember the formulas that go with it. But actually, that's what we call ionizing, because the gamma rays and X-rays, and there's radioactive material as well, which isn't part of the spectrum, they have the ability to cause ionization. So that is, if you think about the basic structure of you as a human being is molecules. Well, they have enough energy to eject electrons from the outer orbit of a stable atom, which can leave it more chemically reactive, and that can go on and lead to a biological effect. So they've got enough energy to do that. That energy drops off as you move into the optical radiation spectrum, which is that bit in the middle. So the bit in the middle is there's a tiny sliver of it which lets us see. So our eyes, although we know our eyes are, we think of them as very sensitive, they're actually not very sensitive at all in the grand scheme of things. We don't see mobile phone signals, we don't see gamma rays, but we just see a little teeny weeny bit right in the middle of it, and we see 7 colors. So you can probably remember the acronym or the saying Richard of York gave battle in vain: red, orange, yellow, green, blue, indigo, violet, 7 colors of the rainbow. We see them. We see different mixtures of those colors as well. But our visual perception is quite limited. But ultraviolet's a big part of it, which is invisible. And infrared's a big part of it as well, which is also invisible. And then we move into electromagnetic fields, which is, again, very different concept. So generally what happens in electromagnetic fields, you create a field, it has an electric component, it has a magnetic component. Sometimes they're related, sometimes they're not. They've both got energy. And then you get waves where a fraction of that energy in a field is radiated out. And we're really clever at modulating the field and then getting a modulated wave out. And that's how mobile phone signals work. We modulate the signal, we code it, we code the field, and that pings out a wave, which we can utilize for communications. When you're talking about ionizing, you talk about energy. When you're talking about optical radiation, you talk about wavelength. When you talk about electromagnetic fields, you talk about frequency. It's just a different notation. But what's the key concept? The key concept is radiation has the ability to interact with material or matter and deposit energy. That's the fundamental principle about this stuff. And what is the differences between them? Well, how that energy is deposited and the effects it leads to can be good, they can be bad. So not every energy deposition in biological tissue is a bad thing. It's just there are certain thresholds which it goes above, but it can be an issue. So when you're into optical radiation, excuse me, as a section itself, as I said, you've got the ultraviolet and then you've got the infrared bit as well. And the effects, the two predominant effects, there are other effects which I won't go into, but the two dominant effects are photochemical in nature and thermal in nature. And ultraviolet is quite a dominant photochemical effect. It's great, and anybody's ever had sunburn will know that. So effectively what's happening is the UV is interacting with your cells, it's depositing, or rather your skin in this case, it's depositing energy, and that energy is leading to a chemical reaction. And that usually is a time frame associated with that. It's not always instant, depending on how much dose you get. So you see that latent kind of effect. So that's why when you go for, when you're on holiday, you're lying by the pool, you're having a great time, this is fantastic, and then you go and have a shower later and go, my shoulder feels a bit awkward. And that's effectively what's happening there. But then the two effects kind of in the middle, they do dominate. They do interact with one another. They're prominent. They're still there in that kind of visible region. And the infrared is all about thermal, really. It's about that energy being deposited, which leads to a burning thing. Now, why does all this matter? Because actually, if you want technology to do things, you're looking at the effects. So you might have a laser which is used to cut something in your workplace. Well, you want something that's in the thermal region. So you pick your wavelengths accordingly and you go for that. What's the most effective mechanism? And this is a real impact on us going forward, because if you think about light technology as well, that's changing all the time. The old days used to be you'd have an old incandescent lamp which would produce a whole spectrum. But nowadays you might have a bit of blue in that, which will cause a photochemical potential reaction or photochemical changes in the retina. And things have changed quite a lot. Now, EMF, by contrast, is a bit different. So that frequency covers quite a big range. So, and the effects can be different as well. So when you're at static, so zero frequency, what you've basically got is we don't really talk about electrostatic fields because they don't really cause a harmful effect. So we tend to talk about static magnetic field. And what happens is because you are moving in a static magnetic field, that leads to effects on your central nervous system. So vertigo, nausea, and so on and so forth. And that can be a bit disorientating. So if you think about MRI machines, they're quite intense fields when you're in those areas. And as the frequency rises, and now we're into kind of power generation sort of frequencies, its effects on the central nervous system. You almost think of yourself as a big bar of metal, and you're inducing currents that are running through you, and that's affected your central nervous system. So similar to static, it's just probably a bit more pronounced. And then you're moving into radio frequency, which all becomes about heating. Yeah. And the middle kind of frequencies there, you've got the whole body's heated. So that's the big thing about radio frequency. It's the heating of the body, heating, thermal overload. And as you move up into higher frequencies, that's about heating the penetration of the RF radio frequency, or the EMF doesn't go as far into the skin. So it's actually the surface layer of your skin that are heated. And the way you've got to think about whether something is a risk or not is really down to the two things I've mentioned right at the beginning, which is the direct effects. So that is where the NIR is directly impacting on your body, and that's having an effect. So it's that energy deposition, which is going on to lead to a biological effect. The second type of effect is indirect. So it's either interacting with an object, which is then having an impact on you. So it's not directly impacting you, but it's having that kind of secondary effect on you. Or it could be something that's associated with a product, a device, which is there because you've chosen to have that device there, and that impacts on you as an ancillary piece of equipment. So those are the two kind of effects we look at. And then you've got employees at particular risk, because as much as you want to protect people, there are individuals in the workplace. We're all just so different. and we've all got different challenges. And there are people in the workplace who can be vulnerable to certain types of NIR. And I'll go through those a bit later, just now actually, on the next slide. So direct effects from optical radiation. So with optical and an EMF, optical, the two organs that we look to protect are the eye and the skin. So there's, unlike ionizing radiation, we're looking at the insides of the body and tissue and organs and all that. Really, these are the two primary organs we're looking at. And I know I've called skin an organ, but I can't see it as an organ. So the eye is obviously way more sensitive, and certain wavelengths of optical radiation can penetrate through to the retina, like infrared A, which is invisible and visible, obviously. But things like UV can cause damage to the cornea, and it can cause damage to the lens as well. And for those who know about welders, will be very familiar with arc eye and all those things. But also the skin can be damaged. It takes a bit more of a punch, but you can still cause damage to the skin. And of course, UV has been known to be a carcinogen as well. So, if you look at natural UV exposure and the number of deaths a year in the UK from UV exposure to the sun. And then the indirect effects from those can be a range of things. There could be, you could have an electrical issue associated with this. So, could have an artificial optical radiation device, which has a high power source. So you've got the electrical issues, you've got chemical. Sometimes things like lasers can have a chemical laser head, so there's a toxic material there. Or when they're cutting or ablating things, then you can create hazardous plume, which you might have a production line somewhere where you're etching barcodes and marks on your products. Well, actually there'll be a plume, kind of an LED type system there, which will extract out that plume. And there's all sorts of things in there. And of course, one of the things that you do think about when you're dealing with what we call class 4 lasers is fire. So class 4 lasers have the potential to ignite products as well. So just be mindful of that. You always have to think about these things. In terms of artificial optical radiation, the only real time we worry about employees at particular risk is when somebody's skin is potentially more sensitive to UV. And that could be because it's something to do with their skin, or it could be something to do with medication they're taking at the time. And medication's a bit of a tough one to read, really, because you have to look through the information and try and figure that out. But often the premise is, well, actually, we shouldn't be exposing anybody to hazardous levels of UV anyway. And that's the concept, is that risk thing, which I'll come on to as we go through. Now, I will warn you, EMF is a lot more complex than artificial optical radiation. Basically, what I mean by that is you saw those different effects, the nausea, the vertigo, the effects on the central nervous system, and the heating. The effects, obviously, as we mentioned, are those direct effects on your body. The problem that you've got with a lot of this area is how do you assess it? And I'll explain that in a little while. But the indirect effects associated with EMF are really things on the effects on the pacemakers and a whole host of things, which I'll show you in a short while. But also projectiles. So certain static magnetic fields above a certain strength have the potential for things to fly and be attracted to a magnet. And all you have to do is really Google or look on YouTube for projectile risks around MRI units, and you see things like wheelchairs flying across the room, and it can be incredibly dangerous in those situations. And as I've said, you've got employees at particular risk in terms of pregnancies. Is that affected by EMF? It's a really difficult thing to answer because of the nature of what you're dealing with and the sensitivities of what you're dealing with here. So often when you're trying to implement an EMF policy or something, this is a real area that you do need to get a bit of support from a HR department, something to see what can I ask, what can we do, and so on and so forth. And obviously the pacemaker thing I've mentioned before. So in terms of legislation, where does it all come from? Well, it doesn't really matter the fact that we're in the UK. It actually is all internationally derived anyway at the moment. So we have the International Commission on Non-Ionising Radiation Protection, which is a collection of the best scientists out there who review the science. They're independent of any organisations which have a commercial interest, and their job is to review all the science. So that's a lot of data they review. And then what they do is they make recommendations based on that. And the recommendations are picked up by a number of bodies, including the European Union. And that's where we got the legislation for EMF and optical from. So for those who are very familiar with the physical agents directives, well, effectively, this was EMF and optical were two of the four, so noise and vibration were the others. And that's what led to legislation. So the European Union producing those directives, which led to the HSC producing legislation in this country. And the interesting thing is what's going to happen going in the future if things change in terms of the science and so on. So we have that science in the background. It is backed up. And I think one of the key things to remember about the legislation is it's all about acute effects. It's about short-term effects. It doesn't cover long-term effects of exposure. And one of the big challenges, certainly with EMF, is the data is constantly evolving. If you think about technologies and EMF, and there's no evidence of long-term effects of EMF, but obviously people are quite sensitive about things, and you do see quite a misunderstanding amongst the public about mobile phones in particular and mass and things. So the legislation itself, that's the statute numbers that are there. So key things to get across in the optical one on the left is it covers lasers, which it calls coherent light source, and that's to do with how a laser is made. I'm not going to go into the physics of it, but effectively a laser is quite a focused device which produces a focused beam, and typically that beam is one color, and I'm not saying color that's visible, it could be invisible as well. Whereas a non-coherent light source is really a lamp or a lamp system, so it's quite divergent, usually quite divergent, and it can have a whole load of different colors and wavelengths which are produced, some of them which are invisible, and I'll show you a few of that later on. And it covers that thing. The key thing about the legislation, it covers artificial optical radiation at work. It does not cover natural sources, so it doesn't cover the sun. And I mean, that's a different story. But actually, so anything that's an artificial source. And like noise and vibration, it introduces a system of exposure limit values. And the key concept of that is, are you above it? Are you below it? What are you going to do about it? And I'm going to refer to control of artificial, et cetera, as AOR10 from now on. On the converse side, which is the EMF side of things, that obviously covers static as well and right up to those high frequencies. And again, very similar to optical, it introduces a set of exposure limit values, but it's not easy. I'll explain that. There's a whole lot of sub-thresholds and so on and so forth, which I'm going to try not to lead you down the garden path on going forward. So let's look at AOR10. I think AOR10 is a very straightforward set of legislation, and there's no real ambiguity in it. One thing that is in AOR10, there's no exemptions, and that's a key thing to remember. So the legislation itself does not exempt you from a source, but what it does, it doesn't do it in the legislation, but what you can use is industry guidance to evaluate whether you want to, if something falls within a set category, whether you can risk assess it or not. And I'll show you what I mean by that later. So what it does as a concept is introduces the limits and goes, okay, these are the limits, off you go, which are the exposure limit values, thou shalt not exceed. But then the key bit is the risk assessment. And I think a lot of employers miss this bit. What it actually says to you, you have to do an assessment or a determination by calculation or measurement whether you are above the exposure limit values. And then, based on whether you're above the exposure limit values and the risk associated with it, you must attempt to eliminate the risk first. And a lot of organizations miss that bit because they get hauled into the gung-ho of risk reduction. Risk reduction comes after you try to eliminate it. And that's where the obligation comes in. And there's a bit about training. There's a teeny weeny bit in there about health surveillance for if people are working around things like UV and for skin, but nothing for the eyes. By contrast, the EMF X is a bit more complex. So what it does, it has the same start point, which is the limits, and it introduces thou shalt not exceed the limits. However, it complicates it a bit because it jumps straight to this middle bit here, which is called the exposure assessment. So what it says to you, before you even do a risk assessment, you go on and do all those things, you need to have a look and see if your sources of EMF exceed the exposure limit values. Can they do it? It's not asking you to do a risk assessment. It's saying, go on, have a look. Do your sources exceed it? And there's a number of ways you can do that. Obviously, a lot of people are very interested in measurement, but actually measurement is often the last thing you do. You do a paper exercise, you look at what's in your workplace, and you start going through the list of what you think is dangerous and working your way through. And if you are above an exposure limit value, then the law requires you to do an action plan to try and bring yourself below them. And then you do a risk assessment if you can exceed the exposure limit values. And that's where the risk assessment looks at the things like indirect effects as well. And then the obligation bit comes in, the hierarchy of controls and so on and so forth. And then training comes in. So it's kind of like a two-stage process with Chem 4, as I call it. But there are bits in there which can actually lead you one way or another. And it's about being really clear. I need to figure out if I've got anything that's dangerous on my site. And that's always your first step with this. But there are exemptions in this one, which there aren't in the optical. Sorry if I'm confusing you. And really, there's exemptions within the main body of the legislation, which is really for those working in healthcare around MRI units, and also those in the armed forces. Because obviously, if you're working in the armed forces and you're near a radar, the last thing you can worry about is whether you comply with the law or if you're in combat. So it's about that aspect as well. But there's also an exemption certificate, which looks a bit like that. So that one was issued in 2016, has been updated. And what the HSC have done is given an exemption for certain categories of work. So you see, obviously, some manufacturing items there and MRI for research as well. And what does the exemption do? The exemption effectively says to an employer, you don't have to comply with that top bit. So it says, we know that there's limits, but you don't have to comply with them, provided that you follow certain conditions, which is to make sure people's exposure is as low as reasonably practicable. And I think part of it is because we have certain uses of EMF for which there's no other option at the moment. There isn't an alternative to turn to at the moment. And it's trying to make things as safe as possible. So apart from the stuff that's in the main legislation, this stuff gets reviewed, this certificate gets reviewed every 5 years. But you still have to do a risk assessment. You still have to do training and all those things. So let's go into optical again. Let's looking at the limits themselves. They're pretty straightforward. They're all wavelength dependent. So it's not like one dose for everything. What it's looking at is the different wavelengths have a different corresponding limit, if you were. And there's different limits for lasers, and there's different limits for broadband sources. Now, in terms of safety in optical radiation, the laser kind of safety element has been built up for 60 years. We've been building that up, and I would say probably the legislation's catching up with that. But actually, there's a really good set of laser safety standards, which are, I'll refer to them in a little while, and they refer to maximum permissible exposures, which is pretty much exposure limit values because they all come from the same place. And there's a similar set, and basically what they're saying to you is you don't go above them. And if you go above them, eliminate or reduce exposure. But it can depend on a number of things. Exposure time, if you've got visible or infrared A, the retinal image that's created on the back of the eye, and all these things can make a difference. But EMF is a bit more complex, and I do apologise for this, because you've got kind of two levels here. You've got the sensory effect, exposure limit, and the health effect, ELV. Now, the sensory effect is effectively saying you can exceed those, provided that if you exceed them, then you update your risk assessment, you let people know, and people understand what the effects are, and they can report them. And a sensory effect is really something that's not dangerous, but it can be annoying. So if you think about flashes in the eye at the lower frequencies, you're thinking about higher frequencies, there's an acoustic effect that can happen with microwaves. And it's actually saying, well, we recognize that's not going to hurt you, but actually it is really, really annoying. And you need to report it. And we've got we update the risk assessment as a result, and then we'll guide you through that process. So you can exceed the sensory effects. And then there's health effects, which you should not be exceeding, which is that this is potentially dangerous to you. And I think that's the key thing to remember. And the key thing with EMF is you either have the effect at low frequencies and high frequencies, or you don't. You've got to be in that field or affected by that wave to get that effect. If you're not in that area, you don't see it. And the big difference at low frequencies, it's instantaneous. Time doesn't make a difference. But at a higher frequency, because it's about heating, time does make a difference. So, I'm not going to make this as easy as possible. I do apologize. But there's a lot of nuances associated with this. And unlike optical, where we can actually go and measure and we can do all the fun stuff of calculations, we can't do that with the majority of EMF stuff, bar static and a few other things. And the problem, as you can see in that image on that top left there, is that the exposure limit values are based on internal quantities. They're based on what happens inside the body. And the problem with trying to do that as a measurement, unless you stick people there and you stick probes in them, which they're not going to be very, very happy with, you haven't got a definitive way of assessing the exposure limit value outside of a very fancy piece of kit and a computational analysis of which costs you a lot of money. So what the regulators have got in the legislation is what we call action levels. And they relate to the exposure limit values. And basically, they're an extrapolation, the worst case scenario extrapolation. And what they're saying to you is, if you stay below an action level, you will stay below the exposure limit value. But if you exceed an action level, there's a call to action. You've got to do more detailed analysis. And then the likelihood you're below the exposure limit value, but you don't know. And that's why it's saying there's a call to action to find out. And there's Paul there in the middle. He's doing an EMF assessment, low frequency magnetic flux density assessment around a chiller unit, which can be on a lot of facilities, and a lot of power generation stuff is generally not exceeding the action levels, although it can affect those with pacemakers. And therein is our next issue. If you park optical to one side, EMF in the majority of cases will not exceed an action level. There are things that can, and I'll share some examples of that, but actually in the main work area, a lot of, especially electric power generated equipment as well, can exceed those kind of really low limits for those who have active implanted devices and body-worn devices. And I'll show you what they are in a bit. And that's the real challenge, really, with EMF, is what do you do with that? Do you go and say, okay, I'm going to block everybody on the site from doing a certain type of activity? Or do you focus on the areas that you know and actually just stop people going into them? And I think education is a big thing here, is you're educating people to tell you if they've got things. And this is why I'm talking about HR, is getting that support as well. And the legislation does not give you limits for these people. You have to go to a separate set of limits, which is called the EU Council recommendation level. So it's an EU document, and that's the reference there. And the types of implanted devices and body-worn devices can be really wide-ranging. And the big difficulty you've got is, unless the manufacturer says, I don't think this is a problem, we've tested our kit and we've tested this implant, which a lot of them are starting to do now, it's really difficult for you to make a definitive judgment. So you almost put everything into three buckets and go, okay, if you've got any of this stuff, we don't want you going into a plant room with this electrical generation equipment. We don't want you working around that welding, for example. You can't do welding. You can't go in that workshop if you've got any of these. But how do you know if it changes? And that's a big thing. And what a lot of the work I've been doing with organizations is getting at that senior level, that management level, getting the induction training right, so you have this stuff in your questionnaire, because you do it for other things, I'm sure, with some of the work that you do. So where do I start? Because that sounds all really confusing, doesn't it? And you're all kind of thinking, gosh, I need a cup of coffee, just getting through those first 20 slides. There is guidance, and it's good guidance, and I'll show you some other guidance in a bit. So the first protocol with any sort of NIR is go to the guidance first. So this is guidance produced by the HSC to support their legislation. The one on the left is for optical, and the one on the right is for EMF. The one on the left doesn't have a number, as far as I know, but the one on the right has a number, which is HSG 281. And HSG 281 is an incredibly detailed document. It actually includes some really good guidance about the effects that we've just been talking about, how to apply them, who can be affected by that, what groups of people can be affected by that, as you've just seen in that previous slide. Also, what's dangerous, what can be considered dangerous in the workplace, and it groups things up. And I think the intention, I remember speaking to the HSE when the legislation was produced, and what they said is they only see 5% of employers being impacted by the high danger stuff. There's obviously a question of what you do with workers at particular risk and how do you protect them. But I think it's that light touch, it's getting things right so that people understand that there is a risk with some things, but not going overboard with it. So that's freely available and you can download them and they're a good read. The other thing to start off with, and you'll see I pushed measurement quite further back because everybody jumps to measure. They like doing measurement, but you don't have to. It's getting that data up front. So manufacturer, please help me. So if I'm in optical world, I've either got a laser or a lamp. There is individual standards. So there is a laser standard, and that's called 608251, the British standard, and it's based on an international standard. So theoretically, should be consistent across other countries as well. And what it does is it grades lasers into different classifications. It starts with class 1, which is right at the bottom there. And what it's saying about a class 1 is it's safe under reasonably foreseeable conditions of use. So it could be something that's enclosed, can be a class 1. So it can have a really powerful laser system inside it, but by the time the manufacturer sold it, they've enclosed it. And that might be something on your production lines. If you've got a production line, you've got a laser system on there, that could be a class 1, even though it might have a really powerful laser. And it works through all the classifications until you get to really the two that give you issues, and that's class 3B and 4. So 3Bs are limited at about 500 milliwatts, and they can cause injury to the eye, but they're safe to the skin. Class 4s are completely unlimited in power output. They can do what they want and what the manufacturer wants to set them to. And they can hurt you. They can have cause optical injuries, skin injuries, and they can set fire to things theoretically as well. So it just gives you, that's your first port of call. And then you look at the guidance and you go, okay, I need to do a risk assessment clearly for this, and you work your way through. Lasers is pretty straightforward. And as I said, we've got a lot of good structure around laser safety in the UK. Lamps are they're a bit more difficult to assess. And the reason why lamps are harder is because we haven't got that infrastructure behind us that's built up over years to try and assess it. So lamps have an individual standard, which is 62471 IEC or BSEN 62471. And they grade lamps into different risks. And really the one you need to think about is risk group 3. So that's the stuff that is supposed to pack a punch. So that's typically things like a UV sterilization system. You might have a water purifying system, something like that. You might have it in a facility. Manufacturers can get it really right. And when you get stuff right, it's fantastic. So on the EMF side, you really want to figure out what your extent of field is. So for example, and I'm going to take you slightly possibly away from what you typically do. So this is an example of a PET MR, what we call, so it's really an MRI on the left. And what it's doing is it's the manufacturer's giving me a lot of data. I'm going, okay, so you can see those like lines kicking out across and coming out radially and so on. And you think, okay, great. So I know what the field strength is, and that doesn't change because it's a fixed installation. But what they didn't tell me was that red line, which is the way the pacemaker people get affected by. Well, that pings into another side area that at the top then. I didn't think about that. Oh dear. And one of the big problems with static magnetic fields especially is that shielding doesn't really make an impact. There are certain shielding materials that can, but actually distance is your big friend here. So you're having to think, well, what am I going to do? Is that an office area? Oh, right. I'm going to have to move all those people out there and move them away and so on. So manufacturers can give you a lot of information. On the right is what we call a nuclear magnetic resonance device, an NMR. You might have that if you have a chemistry type laboratory and you're doing sorts of chemical testing, and you might have one of these big kind of units there. And that will produce a field as well. And then you look at that and you can judge how far you need to be from that. And you can put barriers and restrict access and so on and so forth. So that's where manufacturers are brilliant at helping you. That if you get a good manufacturer, it's worth its weight in gold. They help you quite a lot. Then they can have not so great manufacturers. So this one is for a what we call a little innocuous piece of kit. I'm not saying they're all dangerous, It's just every so often you can come across things which would be hard to figure out the dangers, and that's just the only little section you got out of this manufacturer's sort of instruction manual. So don't get within 24 inches of this device if you've got a pacemaker. But this thing they've got 50 of these across your site. How do you deal with those? And actually, when we did some measurements, what we found was it wasn't just the pacemaker people were affected within 20 centimeters. So this thing on full whack doing what it's supposed to do, but actually we breached for this particular piece of kit on this particular occasion what we call the low action level. So that sensory effect was exceeded within 10 centimeters. Now, what's the company's response to that? Systematically labeling, systematic improving its laboratory induction areas, and just saying there are certain equipment that can affect certain people in here. And if you have any of these items, you should tell us and we'll try and protect you. And I think, if something is really risky, you take it out of action. And it can be the same with lasers, less so, but actually UV can cause us huge problems in the sense that the way that things can work. So this is a Trans Illuminator. So I showed you that at the beginning. So two different laboratories in the same building, and on the one on the right, it's got the protective kind of perspex UV screen, which should be used all the time, and the one on the left side, one that's broken. So there's UV coming through the one on the left, and less so on the one on the right. So very much focused on administrative control. There isn't a lot of engineering elements for this, which is a real shame. And the manufacturing data does not help at all. Because the manufacturer says, look, it's a benchtop device, it's a powerful source of UV, it can cause damage to your eyes and skin, you should have protection. What does that actually mean? That's where it's challenging manufacturing. That's not good enough. You've got to tell me what grade of protection do I need? Why do I need that? You can't just tell me I need protection and that's it. You have to help me out to understand why I'm buying this piece of kit from you. And it's not just something that looks great. Sometimes you can find things that you think, oh, I didn't think about that one. And an example of that is a laser cutting device. This was bought. This is a workshop where they cut plastics and they cut all sorts of stuff into little small components. So you've seen kind of laser cutting devices used in a lot of manufacturing. And actually on the right, what we noticed is actually it's not made to a British standard. So even though it looked like it looks all really nice, actually what we realized is that it was bought from a country where they didn't apply the British standard or even the international standard. And actually the interlock systems when the hatch open were just magnetic interlocks and position switches, which you could easily defeat. And it defied the purpose of what you're trying to do. And anybody's worked with interlocks now, they have to be robust. And so we condemn this piece of kit. So you can go to the manufacturing data and you can get a lot of information. And really what I would always say to you is always go and do your manufacturing information first. Don't jump straight to measurements, because measurements are complex and you really need to know what you're doing. There are broadband equipment which you can buy, some examples there that we've got. And what I would always say is have a think before you commission any measurements. And so Angela and Fernley on the bottom left there. So Angela's got what I've got in my hand. That's a really good picture of me because you can't see me very well. I've got a device which is used for measuring time varying magnetic flux density. And Angela's holding that as well. So that's kind of the lower frequency. And Fernley on the left there's got something for higher frequency. One instrument doesn't cover everything. It doesn't cover every wavelength. It doesn't cover every energy, it doesn't cover every frequency. And that's the key thing to remember. You do need to know what you're picking up and what you're going to measure. Because as you've seen with the biological effects associated with EMF and optical, they all change. So the equipment has to be able to adapt. And you might need to spend a fortune just to have different frequencies and wavelengths covered. And the thing with measurements, you can get them really wrong as well. You can under measure things, you can over measure things. And there is, with some instrumentation, there's a lot of prone to error associated with it. And also the other thing is you don't know when something is working. So what you can do, if you're in optical, you can actually just avoid the measurement argument altogether. You can go straight to, excuse me, And calculations, if you are mathematically minded and you like your maths, then you can use 608251 for lasers and 62471 for lamps. They are the British standards. They're there for assessment. Use them. So you figure out various things and you go and figure out where you are in relation to that. But you got to know your maths. Some of us are good at these and some of us are not very good at these. I'm very thankful I've got a great team around me, which are fantastic at doing these calculations. So that'll give you the answers. You don't have to do any physical measurements. If you are going down the measurement route to do this, be really careful about what you want to know. So what are you measuring? So is it the photochemical elements of a lamp? Is it the thermal elements of that? Is it both? In EMF, are you measuring electric field? Are you measuring magnetic field? What frequencies are you measuring? Do you have to think about the other things like contact currents, which can happen? And that's that question, do I need to measure at all? It is not a legal requirement in the EMF regs to measure. Not a legal requirement. The HSE has not made it a legal requirement. They want you to do an exposure assessment, but that does not make it a mandatory legal requirement to measure. And I think part of it is that the HSE have always recognised that it's difficult to do. So myself on the left there, I'm doing measurements in a plant room around substation, electrical distribution equipment. And what I'm focusing on there is at the top, which is that big kind of tied in electrical cable, which I know will be drawing a lot of current, and that's producing a magnetic field. Fernley on the right there is during COVID, he was doing an assessment of a blue light lamp, which they use in neonatal lamps. So you see them, little babies in little neonatal beds and the lamps on top of them. So he's assessing that with spectrometer. Starting with optical, the real first challenge is, which bit are you looking at? So you might have a lamp. So I said lasers, generally we don't measure, we use the calculations. But if you're looking at a lamp, they can kick out all sorts of wavelengths. So you've got bits which will start off in the photochemical, and then there'll be a thermal element, as I said. Do you know what your lamp is kicking out? That's the first thing. It's having that information for the manufacturer. So what wavelengths are you covering? Where's your principal wavelength? What is the emissions that are coming off this lamp, please, before I assess it? And then you're looking at that, and then you've got to figure out, have you got equipment to do it? Because a lot of people do brightness measurements, candelas, lux, and so on and so forth. But the problem with doing those types of measurements, they're triggered to the response of the eye. And the eye is not uniform in when it sees bright light. So it has a better response at green than it does at red. So that's what we call a photometric unit when you're measuring that. What you need to do is do radiometric assessments, where you're looking at it just on energy, irradiance, energy per unit area, effectively. That's what you're looking at. And these spectrometers are brilliant. You can, like I said, broadband things, but they'll measure across a range. So you've got to be really clear about what you want to do. If you're going down the narrowband measurement, this is an example of a narrowband piece of kit, which measures UV and visible, and we'll get a spectrum out of that. And then we can compare that to the spectral response. So this particular manufacturer of the lamp it is centering around here, but there's other wavelengths that are created with it. And what our team will do is look at that response across the entire wavelength and compare it to the exposure limit values. Because one of the big challenges in optical is that when you change wavelength, you have different weighting factors. So some parts of the optical spectrum will have a higher weighting factor than lower, because you're more at risk in those areas. So you have to assess. It's almost like you've got a whole load of dose limits that you're constantly having to assess against as you're going through. And bingo, from that you get your answer. But I know plenty of people who make mistakes in this area, and it can be, as I said, quite complex. So that's optical. EMF, and again, I keep on saying this, EMF is quite complex, and it can be quite complex. It's because when you're in EMF, rather than looking at illumination for optical, what you're actually looking at is two components: electric field, magnetic field. And they change on two premises. They change on distance from the emitter. So they have this thing called a near field and a far field. Near field is where you've got a lot of stored energy. Far field is where you get less stored energy, but more radiated energy coming off it. So you have to know where the near field, far field boundaries is. But more of an issue is the way the electric and magnetic fields behave. So when they're at static and medium frequencies of power generation, that sort of stuff, what's basically happened is there is no correlation between the two. They exist and they're connected to one another, but actually the properties of one are very different to the properties of others. So when you're in that kind of frequency region, you have to measure them independently and make a total assessment of what the issue is. And that's what I mean by that couple there. They're connected. They're clearly connected because they're on a date, but they're quite independent of each other because they're on each other's phones and not really paying any attention to each other at all. So at low frequencies, yeah, you really need to think about doing them separately. And your kit has to be able to cope with that. You have to have an electric field probe and magnetic field probe. At medium to high frequencies, it's a lot easier. And thank goodness for that, because actually what happens at sort of medium to high frequencies is that there is a phase relationship between the two, and then they start to relate to one another. So actually, by doing measurements of electric field, you can figure out what the magnetic field is by utilizing things what we call the wave impedance equation, and working back through electromagnetism, you can figure out the total energy of the emissions, and one measurement will give you the answer for the other one. So again, it depends what frequency are you measuring at, and can your kit cope with it. The other thing at lower frequencies, especially when you're dealing with power generation, to think about is what we call harmonic content. So that is because if you think about electric supply in the UK is 50 hertz, but obviously that's not just a perfect waveform. We connect things like transformers, which have got a kind of a non-linear type connection to those, and that really messes up your harmonic, your waveform if you want to sinusoidal waveform. So you get multiples. 50 hertz, which can get us say 150 or whatever. And actually what the problem there is, you're having to assess all the different frequencies. So that is effectively what's happening in this here. So Fernley on the right and Robert on the left are assessing magnetic flux density created by the pump on the left and the electric cabling you see Fernley's very close to on the right. And what that kit is doing is not just doing one frequency measurement, it's doing multiple frequencies. And it's so clever, it's just figuring it all out in one go and giving you a magic number. And that's the thing is, in the old days, you'd have to go and measure, you'd have to go and buy something which could do individual frequencies. But nowadays, you can buy kit that can do the whole lot in one go and give you an answer as a percentage of the exposure limit value of the action levels. And there is stuff out there. So things like welders, which is covered by an exemption, resistance welders. When you're looking at that equipment will say to me, well, the low action level, which is the sensory effect, is exceeded within 30 centimeters when the weld point is created. So the thing comes on, then the field is created. That's where the exposure starts. So in this one, the high action levels, which is the health effect ELVs, were not exceeded, but the low action was. So that means I can breach that, provided that I do the risk assessment. I do, I let people know and warn them and train them how to recognize those effects, etc., etc. But the big issue with that piece of kit in that particular instant was that the pacemaker levels were exceeded within 1.5 meters once the weld point happened, and it's instantaneous effect. So I'm thinking about, where is this thing positioned? Is it by a window? Can people get around the other side of it? Are they having their picnic there in the sunshine, the other side? Well, I just want to bar people from coming into this workshop as a result of that, if they've got a pacemaker and one of those other objects we talked about. But it's covered by an exemption, and that's so you don't have to comply with the exposure limit values. As I said, you have to comply with the sensory effect ones in this case and train people. And obviously you have to keep people out who could be affected by it if they're sensitive. And I think it ultimately goes back to the fundamental principle of risk and implementation of control. It's trying to get the whole thing across. And it all starts with the risk assessment. So your exposure assessment feeds into your risk assessment. And that's the mindset to think about, is you can't really do a risk assessment if you've not done an exposure assessment, whether that's on paper or whether that's using some assessment methodology. You have to start somewhere. And that's typically where we're going with this. And it's also thinking about normal and accident situations, but really importantly, the life cycle of an equipment. So you might find that you've got something which is quite hazardous on site, which is enclosed. And it's great because then, the risk is easy to manage, and you're eliminating the risk if you can't get to it. But what happens during a maintenance activity, then the whole element of, well, actually, I've exposed this source now. I'm having to manage this. The person who's coming out, who's working on the permit to work system, they've got to comply with the regs as well. How do I get them to comply with the regs? Do they do their exposure assessment? How do we work together to do it? And that's where the complex bit, I think, comes out of this. And it's trying to get across to people the whole engineering argument, the administrative arguments. You're all familiar with this. But one thing that the HSC are very, very clear about, certainly for the laser element of it, there needs to be a justification why you've got open beams. It's not acceptable, certainly when you're dealing with lasers, to have powerful open beams. If you've got low-powered beams that don't affect you, fine, but high-powered beams, yeah, absolutely. There has to be a clear element of trying to eliminate that exposure. And sometimes some of the control measures you put in are a double whammy, because actually they can, by doing one thing, they can do another as well. So if you think about welding, and we're thinking about the optical thing and the EMF thing, so maybe the welding point, because you're going to get quite a strong magnetic field around that. Does the, is thinking about the procedural control. Does a welder really need the kind of, the cables running over their shoulder because of the effects are in the central nervous system? You think about the trunk of the body. And the Welding Institute did provide some really good guidance and support in this area. Really, really good stuff. And they were involved quite heavily when the regulations came out. But on the right there, well, actually, if you've got optical curtains, they're doing two things. They're doing protecting people from the optical effects, but they're also keeping people out from the EMF levels as well. And that's the key thing. You don't ever really want welding in an open environment where people can walk in because of the optical and because of the EMF side of things. And typically what we find when we're out and about is just a real mixed bag in terms of what we see. And this is what we see in a research facility. They can, on occasions, completely bypass the engineering controls and the administrative controls, and the over-reliance on PPE is just, it's always been there, and it's trying to get research to catch up with industry a lot of the time, and that's sometimes we have issues with. And in this individual thinks they're completely safe, but they're only protected by a pair of goggles from a device that can blind you, burn you, and set fire to things. Some people do try, they do recognize that something's dangerous, but it's how they come across that. Often we find something like this, which is a big sign which says, make sure the power is switched off before you walk in front because it hurts. Now, for me as an auditor and a health and safety professional, I'm looking at that thinking, it hurts. Why have we not done a risk assessment about this? You can't just put a sign up to say it's going to hurt. You're clearly breaching an exposure limit value or something here. We need to find out what this is, and we need to implement stronger controls. We do get things right, and you're probably wondering why we've got strawberries as a picture here. Everyone loves strawberries, well, as far as I know, unless you're allergic to them. But a company approached us and said, we've got this novel piece of kit, and it's amazing when you try from the beginning to set up control measures, how effective they can be. So they said, one of our biggest problems with these strawberries is fungus and fungi and all the pesticides we have to deal with, and we don't want those pesticides and so on. So we want to come up with a UV system, but we recognise that UV is very dangerous to human beings as well. Certainly the levels that we're talking about, we want to kill off fungus and bacteria and all those things. So they generated this piece of kit, which is a robot. And you don't have to get a robot, but I just thought this was really clever. And what they did was the robot scans and goes up and down the rows of strawberries. And you can see the UV tubes on the inside, can't you? And they're illuminating the strawberry plants and treating them. It moves quite slowly, but it's recognizing the different rows. It knows to turn around. The controller can control it from a distance, doesn't have to be involved. It does have sensors on it too, so it knows when people are getting close. But also what was brilliant about this is the manufacturer, when they made this, spoke to the people who supplied the lamps, and they came across with that map there because they didn't need to always do measurements. They had the data, which you can validate. And it's brilliant because it tells me that, 2.4 meters away, ideally 5 meters away if you can, just don't get close to this thing. And you don't need to because it's all automated. There are challenges in NIR safety, and those challenges are everywhere. They've been around for a long old time, and it's personnel, it's different mindsets. You might have a really good facility, you might have a really poor facility in terms of people doing what they want to do. We don't judge as an organisation. Equipment control is one of the hardest things. People buy things all the time, and it's because a lot of this kit can be quite innocuous. I think people recognise lasers pretty well, but the other stuff, I find it really, really hard to pick up. You can have a strong personality. That could be a production lead. That could be a research lead. And they want something done. They've paid good money for this. We've got this piece of kit sat there. Why aren't we using it? And then there's who's responsible for all this. And do people like yourself do it? Is it a health and safety thing? Is it a hygiene thing? Is it a laboratory individual? Is it a production manager? And it's that kind of thing. People can often try and pin that thing on other people. It's been really clear about who is responsible for this. And you do find some bad practices, and don't be afraid to call them out. So this was me on an inspection of a research facility. No entry to anyone on academic health and safety walkabouts, and just locked the room. I had no idea what was going on there, but it's a thing you're drawn to, isn't it? And it's changing the culture. And the best thing you can do is people recognise it. You inform them about what these sources are, and they raise it with you. And the clients that we work for, we're very similar to some of you probably on this call, is that's what they do. They raise it. Your start point is go and have a look at the guidance. If you've not done this before, maybe you have done this before, and I'm teaching Granny to suck eggs and all those things, but actually what you might be the best way to do it is to look through the good guidance that's out there and come up with a plan. So how much of this stuff have we got? You're thinking about the kind of low risk stuff that could affect a pacemaker. You won't capture all that in this initial phase, but what you can do is capture all the really harmful stuff that the HC wanted you to deal with. And you can go through that. And what we do with organisations is we create these sorts of lists, and they go around and unaudit the facilities. And that's where the HSC guidance is really useful, because it does list hazardous sources, but also for EMF, it does list the things that you think could be a risk to those who are vulnerable. So you've got a basis as a paper exercise, as an initial point to start off and work through that. If you want greater detail, you can actually look through what we call the European non-binding guides. So these were commissioned by the European Union when the directives were producing. So in that kind of period of 4 years when the HSC were producing the legislation, incredibly well-written documents. I can't speak highly enough of them. And actually the HSC guidance was based on a lot of content and the outputs from that. So they're translated across Europe as well in different languages and so on and so forth. But the one on the left looks at things like, the gentleman at the computer screen, the photographic lights, and it actually makes a case and goes, well, we've measured this. We don't think this is a problem. But if it is a problem, these are the things you should have in place. And on the right-hand side is the EMF ones, and they come in 3 volumes. The smallest volume is what we call the SMEs. That's a really quick start guide, worth reading. Then you've got the other 2 volumes, which are good practices, but also case studies where they've actually gone and measured stuff like we've been talking about throughout this session. So you've actually got data there, and it's okay to use that data when you're doing an exposure assessment. This is that thing of they've given you all this information. They don't force you to measure when you can use data that's already available to you. One of the key things out of it is training, and what we found throughout, and this is a bit of a self, I do apologise, is kind of how we've had to change training quite a lot over COVID. And actually training is your best weapon in this, I feel, because what it does, yes, it's an administrative control, I realise that, but actually there's an element of you're asking people to think for themselves, and training is always the best thing. And actually, so much has changed with training. You don't have to do it face-to-face. You're all, I'm sure, have got on-demand or basic elements like that on your site where you have induction training. Utilise them to the best of your ability, especially when you're dealing with those pacemaker issues, is have something that's built into your induction so you're raising it earlier on. And this is an example of the laser system, so you can access this on our website if you need to. It just gets the basic methodology. So I'm just going to click this and it should play.
And to visible radiation, but for longer wavelength laser beams, example a CO2 laser, the surface will appear smooth.
And it doesn't take much to do. And it doesn't take people long to watch these things, and you've got them internally or use them externally, but you are educating your workforce to make decisions for themselves. And really, that comes to the end of what I wanted to do. And I hope I've not confused everybody and given everybody a headache, and especially talking about action levels and exposure limit values and so on and so forth. But there is more information on our website about where to go and so on, so especially with regard to training and asking a question. And that's it from me. Over to you, Lee.
Excellent. Thank you very much. So if anybody's got any questions, please do pop them into the chat box or raise your hand, and you can unmute yourself to ask Raj a question out loud. Just give it a moment or two. There we go. So we've got a question in already. What is the material used for the optical curtains? Do the curtains absorb the radiation or just prevent spreading to those on the other side?
Mainly laser optical curtains will have something which will absorb the material, so the laser. So if we're talking about optical, so it can be obviously laser and it can be sort of broadband UV type stuff. So typically when you're dealing with sort of optical things with UV, what you're looking at is something that complies with the various welding standards. So that would be something that absorbs it and doesn't reflect it. With lasers, it's a bit more complex because they have to comply with what we call the British standard, or the IC standard, which is 60825 Part 4, which is a standard about manufacturers who make guarding and curtains and things like that. So what I would say is you want something that absorbs it and doesn't reflect much. But it could be plastic, it could be anything that it's made, as long as it's been graded to the standard.
Excellent, thank you. And then another question's just come in. Do IR lab heating lamps need any shielding or controls?
Depends on the lamp, Lucy. I think it's one of those where when you're looking at them, so the first thing with infrared, what we know is obviously heating. You've picked that up when you're dealing with those. And I think that the key thing is, what is the spectrum kicking out? And that's where the manufacturer, I think the question you want to ask them, Lucy, is does your lamp exceed the exposure limit values within the relevant legislation? And that's what they should be telling you. And because it's heating, they should tell you a time frame that it's going to exceed it to. And I think if there is a risk because it's a heating element, then it might just be a simple thing. Once you've got that information, Lucy, is to put some controls in place. And it's really just restricting access to the area. Because it's remember, you're talking about optical, it's the eye and the skin injuries. Hope that's answered your question, Lucy.
Yeah, feel free to type any follow-up questions if you want. We've got 15-20 minutes or so good bit of time for a few more questions. There's another one here saying, any recommendation for employers concerned by WLAN routers in offices?
Yes, it's a tough one, this, Anne-Marie, and the reason why it's a tough one is, and I've spent a lot of my early career looking at the effects of certainly mobile phones, but also wireless communication on health, and there is no definitive proof that they do. I mean, they're generally low powered, and a lot of wireless routers will be transmitting as well as receiving. What you want to look at, Anne-Marie, is you look at HSG 281, which is that HSC EMF guidance, and what it will do in there, it will give you the ability to put wireless routers in the safe box, the reasonably safe box. And I think that's about the only thing you can do, because what I've found when I've dealt with staff and members of the public, the difficulty is the perception that it's dangerous. And that can have a real impact on you when you're trying to come at it from a pragmatic point of view. So utilize HSG 281 and say, look, the HSC thinks that wireless LAN isn't an issue, and I've never really found any emissions that's dangerous around them, and I've done lots of measurements around them. But there are probably going to be certain people who aren't going to be satisfied by that answer. It's how you deal with that. All you can do as an employer is do a risk assessment, utilize the guidance, and come up with an answer.
Will the PowerPoint be available to share when I send out the link with this as well? Is that something I can share out?
Yeah, well, I mean, I'll probably do it as a PDF. We don't tend to give the PowerPoint, but I can certainly give it as a PDF so you can look through them and watch them. Oh, there's Ian. I haven't seen Ian for years. Good to see you, Ian.
Well, yeah, it'll just take me the afternoon to render the video, chop off the ends, and then get it up on YouTube, so I can send out the link with the presentation, hopefully in the morning for everybody. We've got another question here. To what extent are manufacturers, suppliers of equipment legally obliged to provide information to allow risk assessments to be carried out?
Interesting one, this one, because if you look at, obviously, the UK Health and Safety Work Act and so on and so forth, I would say that manufacturers should be providing that information. And I would argue under the Health and Safety Work Act that they should be doing that. So what I think as a you should be doing, and often the best results we have is we're quite tough with our clients. We go back to manufacturers and ask them to really think about this, is go to them and ask them a very simple question. Does your equipment exceed an appropriate exposure limit value or threshold within the regulations? Ask them that specific question. If they don't answer it, they're not giving you good enough information. Because what you don't want to do is get in a situation where the manufacturer is just saying to you, wear goggles, wear eyewear, wear gloves. That's not good enough to you. You want to know what eyewear you need. You don't want to know what grading of gloves you need. You can't make an adequate risk assessment yourself as an employer if the manufacturer doesn't help you, and give them a hard time over it. Be tough on them. So I would say, yes, they are legally obliged to provide you with the information, because you can't do your risk assessment without it.
Thank you. I don't think, just as I say that, there is one coming through. Any comments, experiences of dangerously high UVC bulbs in exotic pets industry?
Good, really good question, Andy. It's a tough one, right? Okay, so when you're dealing with UVC, you're dealing with sterilization. You're talking about high energy UVC. You're very close to the kind of the boundaries, and when it goes into ionizing. What I would say with UVC is you really don't want any exposure to it. Because if you think about what it's capable of doing in high energy, as I said, it's used for a lot for sterilization purposes, and they're using it in hospitals now to sterilize. During COVID, they've been doing that. I think you don't want any eye or skin exposure of your staff towards it. So you really, Andy, need to come up with some control measures for stopping people getting into that beam and being accessed by it.
Another question through. They're coming in thick and fast at the moment.
Right.
Is there an EMF action level that could be used to assess ignition of explosive atmospheres?
Yes. If you look back through, Rob, if you look back through the notes, I did make reference to standards. So typically what will happen is, if you have a look at, there's various standards which will give you, I mean, there's people who know a lot more about this than I do, but actually you have to refer to the relevant standards to get those levels which are appropriate. And this is a bit of an issue with the military as well, because obviously they can have explosive devices as well. But yes, there is, Rob.
And while we wait for other questions, and apologies if you've already mentioned it, would Brexit have any effect on legislation going forward? That's a common question. It's always legislation, and then how will Brexit affect that legislation?
Okay, at the moment, no, because both sets of regulations are in our statute book, the statutory instruments, so until we decide to take them out, then they stay. The Brexit thing is an interesting one, because if you think about the European Union directives, light, noise and vibration led to legislation. And the problem that we have is not so much that the European directives are going to lead to further legislation. We don't have to comply with European directives from now on. But the issue is going to be in the long term, where a fundamental technical change with regard to thresholds does not translate through as a legal change. Now, what the regulations do is they refer to the directive, or they refer to standards. They don't always have the values within the legislation itself. So my understanding of this when Brexit happened, because I helped write a paper on the EMF position for the Society for Radiological Protection, which has done some work on this. And what we came up with is we don't think any microscopic changes to thresholds will lead to a macroscopic change in safety. And that sounds a really cop-out answer. But basically what we're saying is, even if things are tweaked a little bit, that won't necessarily mean in a working environment there's going to be massive changes. And I don't think there's a desire from the HSC to change anything, unless HSC is here, of course, it might answer that differently. But the regulations stay for now. And I suppose the argument you could have is they've always been there, they've just not been specific legislation.
Thank you very much. Just having a look, there's nothing new that's come through. So just give it another moment. If you do have any other questions that you think of later in the day, you can email myself at marketing@bohs.org. I can pass any questions on. Did you have an email address on your slide deck as well there?
Sorry, Lee, you're aiming at me?
Yeah, sorry, yeah, just if there's any questions. So once I've sent out the presentation, was there an email address on there that they can contact you with if they've got any more questions?
Right at the end of the slide. Okay.
Just give it another moment, and then if not, we can, yeah, we'll call it on this session. Been some good questions so far.
Okay. Thank you, everybody, for listening. I know it's not the easiest of subjects, but I do appreciate everybody sort of concentrating and keeping their attention right through to the end.
Yeah, just to answer your question there, Deirdre, we are sharing the presentation. It'll be shared in a PDF format along with the link to this recording. So I'll get that out once the video's rendered and been uploaded to YouTube. It'll be most likely tomorrow morning by the time it goes out. Cool. So I don't think there's anything else coming through. Like I say, you can email myself at the marketing at bohs.org email address, and I can pass questions on, or email Raj personally whenever you see the email address on the presentation tomorrow. Yep, thank you for joining today, and we've got another webinar coming up on March 11th on noise. So if you just keep an eye out on the BOHS website, you can sign up to any future webinars there. And if there's nothing else from you, Raj, I'll wrap it up.
Okay, thank you, everybody. Thank you for listening, and might speak to you in the future.
Excellent. Thank you for speaking today, Raj. I'll speak to you soon.
Take care.